we talk about limit for sequence. When we say, we mainly talk about real sequence as far as the syllabus of UPSC is concerned. We talk about limit for a function. The function could be either complex or real. You study about the complex limits in complex analysis. You study about the real limits for a real function in real analysis. I'm not going to touch upon any of the topics specifically. I'm just trying to explain the limits and continuity concept. So why do we need to study the limit? We need to study the limit to know the behavior of a function or a sequence where the function could not be defined, or where the function is not defined, but we are curious to know where the function is heading. If we are trying to reach that point where the function is not defined, there are several regions for finding the limit, as in implications or meaning. If we figure out the limit, the implications could be that if the function is not defined here, then let's define the function and make the function smooth instead of having some discontinuity in the functions. Also, by knowing where the function is headed, in real life scenario, what you will try to do is that if the function is not if it could not be defined at all in any circumstance, if it's not in control to define that function at a particular point, then how can we mitigate the adversity resulting from that indefinition of that function at that point? So this is why it compels us to study the limit of a function. Let's say you're designing a robot's arm. And robot's arm has been asked to behave in a certain manner, as in you will be giving some input and it will be performing some action based on the input, the arm, and that action is basically outcome of this input, which will be related. The outcome and the input will be related through a function. But there comes a point where arm is confused to perform the function because of the function's behavior at that point. For a particular input, the robot's arm is confused. What will you do is that if it is in control to define that function at that particular point, what you will do? You will define it. What will you do is that at that point you will provide some extra conditions that if this point is reaching, then instead of following this function, you just give this output. So you did this and you got away with the functions inability to give you any output at that particular point. So this is how it becomes helpful for us to know the limit of a function. So now coming to the definition of limit, what we do is that here, as you can see, let me change the color of the pen. Here, as you can see, you have, what I'm trying to do is that I'm trying to look at the behavior of the function, not exactly at the point where the function is not defined or not giving us any output. In terms of the regular way the function was giving me the output. So what I'm trying to do is that I'm trying to just know how the function is behaving in the vicinity of this point. So what I get to know is that if the function is, if I am looking at it, looking into the vicinity of the point, and also the function is staying within a particular limit, as in it is not deviating much from this L, f of a and f of minus a minus epsilon, or better I would have said delta. I should have said delta to make it easier for me to explain, because this difference between f of x, f of a plus delta and L, we'll be calling that as epsilon. That's why I've changed the name. So if I take the output, if I remain within the delta vicinity of A, I should be remaining, the function should be staying within the epsilon vicinity of L. Both A and delta, epsilon and delta are very small. In mathematical terms, we call it infinite small. You can assume however small a number you want to, and this should remain true. That what should remain true is that this for every epsilon greater than 0. Why we are saying epsilon? We are keeping it as a variable, not taking some number, say 0.5, 0.0005, because we want it to be true for every small epsilon. Hence, we are not fixating to a particular number. For every epsilon which is small and which is greater than 0, there should exist a delta epsilon, delta greater than 0, which delta is for every epsilon greater than 0, there existing a delta greater than 0, which means if for every epsilon, what I'm trying to say is that, just look at this side note. When we say for every x there exists a y, it means there is some relation between x and y. You'll give some input in form of x, it is resulting you some y. It means y is nothing but a function of x. Similarly, if there exists epsilon, and for every epsilon greater than 0, there exists a delta greater than 0. It means delta, which is a function of epsilon, is greater than 0. If this is there such that fx is remaining in the epsilon vicinity of L, then x will remain, fx is remaining in epsilon vicinity of L for every x in the delta vicinity of A. Right? So then we say that limit is existing, as in we are we'll be able to find a number where the function is functioning is would have headed, would have reached, would have where the function would have reached, or the value the function would have attained if things had been right at x is equal to a also. So this is the definition of limit. Coming to continuity, we just add one more point here. What we do is that if that limit had been equal to a, if that limit had been equal to f of a, not a, f of a, then we say that the function is also continuous at that point, as in there had not been any abruption at all in the movement of the function from a minus delta to a plus delta. There has not been any discontinuity for the function in moving from a minus delta to a plus delta. So that's it with respect to concept of limits and discontinuity.